from Earth. It's Space Radio. This is Paul Sutter, and coming up, we're talking about counting all the photons and, of course, taking listener questions about all things in the universe, because that's exactly what this show is about. We record every Thursday at 4 p.m. Eastern, so call 888-581-0708 to join the conversation. And in today's Blue Shift, I'll be talking about the Fringe. Yes. But first, the news. Hello, space fans. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State, chief scientist at COSI, and for the next half hour, your agent to the stars. Got an exciting show for you today on Space Radio where we talk about all things in this beautiful universe of ours. This show lives on listener questions. We record every Thursday at 4 p.m. Eastern at WCBE Radio Columbus. So call 888-581-0708. Get those calls in. You can also follow along with our loyal and lovely space cadets on YouTube and Twitch, joining in live from Lancaster, California, Ashburton, New Zealand, London, Kempner, Texas, Allentown, PA, sunny East Bay of California, and the Pittsburgh Bull Planetarium. Get those questions there. I'll take questions. If you give me questions, I get you answers. That's how this works. It's a very straightforward arrangement. Go to spaceradioshow.com for those links. Seriously, folks, I've prepped 10 minutes of show material tops. So get those calls in. How we doing, space cadets? I know. This is beyond low res. This is bad. So I'm in Santiago, Chile. I'm on hotel Wi-Fi. I am running the show off my laptop. I don't have my Greg with me. So you got to bear with me. It's going to be a little glitchy mess. As long as you can hear me and the audio is getting through, then we'll be good. So give me some sort of sign that you can at least hear me. My camera is not broken. Yamagishi, my camera is great. Good job, camera. It's my face is broken. My 56K modem. It's chugging along all 56K. Oh, man. Okay, audio's good. Video's going to be rough, folks. This is going to be a rough one. I'm probably not going to save the YouTube video, but we can at least talk to each other, right? It's like a phone call. Remember phone calls? Actually, guys, you know what? I upgraded just for you. I've got a shotgun here. I've got two 56K modems running side by side. That's right, 100. I'm going all in. Get your questions in. Use those question mark emoji thingies. Nancy gathers them. How it works, by the way, you ask the questions. I can't possibly keep up with this scroll. So you just keep asking the questions. Nancy gathers them and sends them to me over on a Discord channel. And then that's how I get the questions. So get them over. Use your little question mark thingy so Nancy knows to grab them. Yes, on my Commodore 64. Man, I coded this in BASIC. I spent all night working on the algorithms. I backed it up to tape. We are good. I'll record the first segment and then we'll get some questions in. Thank you, Cerulean. My voice is the most important part. And before we get started here, I wanted to share some interesting bits of news I caught recently. And this is just a fun result. This is a fun paper that came out where, of course, the headlines are totally different than the point of the paper, but, you know, that's life. The paper itself is awesome. The headlines are all about, apparently some researchers counted all the light in the universe, or all the light emitted by stars in the universe. And you know that light is made up of little tiny bits, little wiggly bits that we call photons. And you can count the photons, like 1 photon, 2 photons, 3 photons. You get a bunch of photons together, you call it light. And apparently all the stars in the universe over the course of the past 13.8 billion years of cosmic history have generated, are you ready? This many photons. 4 0 0 0 0 0 0 0 0 0 0 0 0. Yes, I'm going to count all the zeros. 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. Maybe that's a bad idea because there are 84 zeros. That is a lot. That's a lot of zeros. It's 4 times 10 to the 84 photons emitted by stars over the course of the past 13 billion years. It's something like the universe so far has produced something like a trillion stars, and they've generated 10 to the 84 photons, which is cool. I have 2 things to say about this paper. One, that's a large number. Let's just sit back and enjoy. Let's bask in the awesomeness of a large number like that. And the other thing is the amount of light emitted by stars is dwarfed. It is just a tiny, insignificant fraction of all the light in the universe. Most of the light in the universe doesn't come from stars at all. Instead, it comes from something we call the cosmic microwave background. It comes from the earliest moments of the universe itself. It comes from when our universe was only 380,000 years old. Oh, this is a baby picture of the universe when our universe transitioned from being a hot, dense plasma into a cool, neutral gas. At that moment, an immense amount of radiation was released, an immense amount of light. And that light has persisted to the present day, but it's all the way down the microwave, so it's a little bit hard to see. All the stars in the entire universe, the trillion stars to be produced over 13.5 billion years, has amounted, with all that 10 to the 84 photons, has amounted to less than 0.1% of the amount of light emitted by the cosmic microwave background. The cosmic microwave background is by far the brightest thing in the universe. But the universe is large, and the light was emitted a long time ago. And so it's very hard to see, but it is there. You can even see if any of you have old rabbit-style TVs, antenna TVs, and you get a little bit of static, about 25% of that static is leftover radiation from the Big Bang itself. But hey, stars are cool too, all right? Stars also make a lot of photons, so we can't ignore it. But anyway, that's the latest and greatest when it comes to space. It's time to have a conversation. Oh no, audio pauses too? I'm sorry, folks. We'll get there. We'll get there together. Let me know what I got to do. I have to resist the temptation. I know exactly what happens is as soon as I start waving my arms around, which I'm wont to do because I get excited about this, the video just says, no, I'm not doing that. I'm not handling wavy arms. And so it drops out and then that cuts the audio. So what I need to do in these situations, I need I wasn't going to say handcuffs, but I don't think I want to go that far. Just some rope, just some bungee cord. Just hold my hands down, under the table, so I can wave them and do what I want to do without getting the video off kilter. Some people are liking the video glitches. We'll make it a thing. From now on, only video glitches in space radio. We actually have a voicemail today. And so I'll do the voicemail, and then let's see what questions about. Oh, man, so many questions. Okay, Michael Lubeck, I heard about the new dark matter theory. It's crazy exciting. Yeah, wink. I see your winky face. I'm going to get to that in the blue shift, actually. I'm going to get to the blue shift. Don't want to talk about it directly. I talked about it on Weekly Space Hangout last night. How can we get a giant telescope on the moon? Ooh, that's a fun question. So, Harry Miles, I will answer your question, but first I'm going to do the voicemail. And our first question today on Space Radio is actually a voicemail. Greg, play the tape.
This is Sam from Mississippi. I was calling up to see if gravitational waves behave the same way that light does in special relativity, such that two observers in different reference frames will always agree upon the speed of light. Does the same work for the speed of a gravitational wave since it travels about the speed of light? Just wondering.
Hey, just wondering. I love it. That's what this whole show is about. That's what science is all about, is just wondering. So there is never any shame in just wondering and asking questions like that. That is a really fun question. We've come to terms with the speed of light, right? The speed of light is the exact same in every single reference frame, which means even if you're traveling at, say, 90% of the speed of light, and you shoot a flashlight out in front of you, the flashlight will race ahead of you at the speed of light. It's the exact same thing for every single observer throughout the universe. Now, this question is about gravitational waves, which also travel at the speed of light. And the question is, do we see the same things? All the weird and wonderful stuff that we associate with light, does it also apply to gravitational waves? And the answer is yes. Yes, it does. For what goes for light goes for any kind of massless particle, goes for any kind of disturbance that travels at the same speed. The special relativity is grounded in discussions about the nature of light, but you get that from marrying the mathematics of special relativity with Maxwell's equations, with the laws of electromagnetism, of how electricity and magnetism relate to each other. And so light plays a big role in special relativity, but almost as a placeholder, as a representative of what's going on with massless particles that can travel this fast. Anything that can achieve that speed, like light or gravitational waves or anything else, gets imbued with the exact same set of properties. Now, moving on from there in a totally different direction, I have another question on the YouTube from the space cadet Harry Miles asking, how can we get a giant telescope on the moon? First off, why in the world would we want a telescope on the moon? Well, have you ever tried to look at the night sky and you've seen lots of little twinkling bits? You see how that starlight twinkles and shifts around. It's beautiful. It's gorgeous. It's also annoying. You cannot, doing astronomy in an atmosphere, it's like, I don't know, like playing video games with one hand tied behind your back. Like, you can technically do it, but it's a lot more challenging. This is why we love space telescopes so much, because they get rid of all that pesky atmosphere. But space telescopes are limited. Their size are limited by the size of the spacecraft. That takes them up into orbit. It'd be so much nicer to build a telescope in space where we could take advantage of all that lovely airlessness and piecemeal put together the bits that we need for a giant telescope. And the moon is kind of handy. The moon has no air. And so, you know what? We think it just might work. But here's a challenge to building a big telescope on the moon. Big telescopes need lots of glass, lots of heavy pieces of glass, lots of large pieces of glass, lots of mirrors, lots of reflective surfaces. Telescopes are still telescopes, still just polished lenses and mirrors even after 400 years. But if you want to build it on the moon, sure, you can do piecemeal, launch by launch, payload by payload, build up the infrastructure and the facility and the dormitories and the kitchen and the servos and everything else you need, but you still need a big hunk of glass. And getting a big hunk of glass to the moon is going to be very challenging. So optical astronomy, visual light astronomy is still going to be challenging up there on the moon. What might be a little bit more promising is radio astronomy. Radio astronomy is like so easy. If you have a car antenna, if you just have a chunk of wire, you can technically do radio astronomy. And so it's much easier to just get a bunch of chunks of wire up on the far side of the moon and do some radio astronomy. And there are plenty of proposals out there for building a radio telescope on the far side of the moon. And actually, perhaps the most feasible plan out there right now that I know of is something called DARE, And DARE is actually going to be a satellite that orbits the moon that is a radio antenna that's very, very sensitive and specifically tuned to hunt out the first stars to appear in the universe. So, telescope observatory on the moon, that's always going to be a big challenge. Radio astronomy on the moon, now that's something we might be able to see. It's time to take a quick break, folks. Remember that this show is brought to you by you. Visit patreon.com/PMSUD to learn how you can keep this show on the air. And special, big, extra, universal, cosmological thanks to my top Patreon contributors this month, Robert R., Dan M., Matthew K., Evan T., and Helga B. It is your support and the support of all those other wonderful, amazing people that keep this whole thing going. I'll see you after the break. Yeah, Astro B, how about multiple mirrors with actuators? Like their designs. And this is exactly how we're building like the 30-meter telescope or the Giant Magellan telescope. Is it's a bunch of mirror parts that are all segmented together and can wiggle and wobble and act as a single lens. But each one of those has to be big. Each one of those has to be large. Each one of those has to be entirely and very precise. So think of like how much investment went into Hubble or James Webb Space Telescope. Now multiply that by, I don't know, 1,000. And now you're talking about what you would need to build an observatory on the far side of the moon. And another problem that I didn't get into in the little recorded bit, this is just for you guys, is the data. How do you build a giant telescope, you collect tons of light, you get tons of information, but if you want to do something interesting with that information, you have to get it back here where all our computers are and people are and grad students are, and so you can write papers and do the work. So you have to get a pipeline going. And if it's going to be a giant telescope, it's going to record a lot of data, isn't it? So what do? Do you process it on the moon before sending it back to Earth? Well, that means basically building a supercomputer on the moon, which might even be more challenging than building the dang telescope itself. Or do you send it with satellite relays? But satellite relays aren't the greatest at high-speed data throughput, if you catch my drift. So you need a whole bunch of satellites in orbit around the moon, so constantly streaming back data. And oh gosh, that might actually end up being harder than building the telescope itself. So it's not necessarily the facility of the telescope, it's the optics of the telescope and the surrounding infrastructure to make the telescope worthwhile. That's going to be very difficult. You know what? That ended up being a really, really good section. Greg, I have no idea how long it was. I didn't have my timer on. Maybe we can throw that in the show. Who knows? That's what I love about Greg. I just record whatever I want, and Greg turns it into an awesome radio show. By the way, I am remote right now. I am in Santiago, Chile. So no Greg with me right now. How much sunscreen would you need for that initial CMBR burst? Ooh, Brian Street, good question. How do you get Pluto demoted to comet status? Oof. Don't ask Neil, that's for sure. Not going into that one, that's for sure. Ooh, how do we differentiate between redshift due to relative motion and redshift due to the expansion of space? That's a fun one. That's a good one. All right, so I will do, let's go back to that. The Big Bang, the CMB, the sunscreen. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got more Space Cadet questions ready to go. And by the way, if I sound a little bit different, it's because I am not in Studio A right now. I'm down in Santiago, Chile, on my way to the Atacama Desert to lead a stargazing expedition of the best kind in one of the darkest, clearest, driest places in the world. Northern Chile is a hotbed of astronomy. astronomy. There are major observatories, world-class observatories, cutting-edge research happening here. And there are also nice hotels and stuff for staying at, so for enjoying that precious dark sky. These are dark skies you really have a hard time getting anywhere else in the world. So I'm down in Santiago having a good time. Greg is in the studio editing the show, probably wishing he was joining me in Santiago. Maybe next time, Greg. So we got more space to get at questions. We were talking earlier about light from stars and light from the early universe, and got a question here from Brian Street on YouTube. How much sunscreen would you need for that initial burst of radiation that eventually became the cosmic microwave background? You know, it was released when our universe was just 380,000 years old, and it was hot, it was intense, it was an immense amount of radiation, and now it's cooled down, now it's redshifted all the way down into the microwave. When it was released, when our universe was 380,000 years old, the light had a temperature of a few thousand Kelvin. That is something like the surface of the sun. So around the same temperature, that means the light itself was white hot, literally white hot, like a big flash of light at this epoch. And imagine if you're at the surface of the sun, even SPF 100 ain't going to do you any favors. You're just going to melt. But we're protected by 93 million miles of pure vacuum, allowing that sunlight to dilute a little bit before it hits the Earth. But even the part of the light that does manage to hit the Earth can still cause some serious issues. Imagine being at the surface of the sun and surrounded by it. Like every direction, you can't get away from it. Every cubic centimeter of space is soaked in this radiation like olive oil in a piece of bread. You can't escape it. You turn around, it's just more, and you flip over and there's just more. You're surrounded. It consumed the universe. And then as the universe aged, this light thinned out and it cooled off. It got stretched and stretched and stretched. In the present day, this radiation, this fossil, this relic, still soaks the universe, still soaks every cubic centimeter of space. It's just far, far weaker than it was 13.8 billion years ago. But it is still there. It is in every direction of the sky. If you build a microwave antenna, no matter what direction you point it, no matter what time of day, no matter how you break it down, the radiation from our universe, early universe, is still there, still surrounding us. Now, I talked about this word redshift, of how the light from the early universe was white hot, was visible light, but over time got stretched and stretched and stretched as the universe expanded. It stretched down into the reds, and into the infrareds, and then into the far infrareds, and then all the way down into the microwaves where it sits today. And then in the far, far future, it will stretch even further into the radio spectrum. And M. Chupin, I'm giving that a French accent, by the way, M. Chupin on Twitter, one of the space cadets, asked about this redshift. And we see redshift throughout the universe. We see this stretching of light throughout the universe, especially when we look at distant galaxies. When we look at distant galaxies, the light from those galaxies appears to be redshifted. And M. Chupin is asking, now, is that redshift coming from the expansion of the universe? Or is that redshift coming from just like the Doppler effect? Like if you have a loud noise that's moving away from you, that motion away from you will stretch out the sound. It will make that pitch longer. And that's a normal thing, and the exact same thing happens to light. We get red shifting and blue shifting of light from motion. But how do we know when we look at these distant galaxies or we look at the cosmic microwave background, that this light, this redshift that we see is due to something cosmological and not just due to motion of galaxies moving around on their own. Well, here's the thing, and this is what Edwin Hubble discovered that really locked in the concept of an expanding universe. If you go to nearby galaxies, if you look at nearby galaxies, you have a certain amount of redshift. On average, this is totally on average, it's a statistical thing. Of course, galaxies are going to wiggle around, but on average, you look at nearby galaxies and they're redshifting away from us. And then you go to galaxies, say, twice as far away, and you measure their blue shift or redshift, and you get a redshift again, and that redshift is twice as big. And then you go to galaxies 4 times further away, and their redshift is 4 times bigger. And then you go 8 times, and it's 8 times, and 16 times, and 16 times. There's a relationship between distance and the speed at which a galaxy appears to redshift or recede away from us. And the only conclusion we can draw from that, well, one conclusion is, there's a conspiracy. All the galaxies in the universe know where the Milky Way is, care about us, and are trying to get away from us, and in doing so in just the right way, so that a galaxy twice as far away is receding twice as fast, and on and on. That seems a little bit hard to swallow. The most simplest explanation is instead that our universe is expanding. That every galaxy is receding away from every other galaxy on average. And this means there will be a relationship between distance to a galaxy and the speed at which it recedes. That is a very simple, very clear relationship predicted by general relativity, predicted by Einstein's theory of gravity, and borne out by observations. Simple Doppler shift, redshifting of light due to motion, simply doesn't fit the data. Thank you, everyone, for those amazing questions. We're almost out of time today on Space Radio, but before we go, it's time for the blue shift. Yeah, exactly, Brian. Either galaxies are hating on us, and hating on us specifically, or we live in an expanding universe. And I know I am somewhat repulsive, but I don't think I'm that repulsive that galaxies across the universe would conspire to repel away from us. I think they'll repel from everybody else. Just galaxies don't like each other. And yeah, right. You're right, John Michael Gaudier. If there's something that's going to build a giant telescope, it's going to be lithium. All right, yeah, Commander Benkai and a few others have been asking about this negative mass stuff, dark matter thoughts. Let me do my blue shift because I'm going to address that in a sideways way, and then I can hang on longer to talk about it specifically. I need my Greg. It is really hard to run this show without a Greg. Let me just tell you, Greg, you can put that on the air if you want. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get just a little bit closer to you. And earlier this week, I had a wonderful opportunity to give a colloquium at the University of Pittsburgh. And I also, after that, gave a super fun public talk as part of Café Scientifique at the Carnegie Science Center. Thank you so much to Ralph Crew and the crew for putting that together and arranging that. It was a wonderful time. But at the colloquium at the university, I talked about science communication. I talked about the need for science communication, and I created a dialogue. That's what I like doing in my colloquia, is creating a dialogue where I'm just talking like, hey, I'm out here doing a bunch of science communication. You're not. Here's why you should do more. Here's some of the challenges. Here's what I'm seeing out there in the world, in the wild, in my field investigations. And I'm reporting back to my peers what I have found. I brought samples and display cases and specimens, and it's time for us to talk about it. And one of the issues that came up in the dialogue, and when I really get going in one of these colloquia, in one of these discussions. There are no good answers, but it's like just talking about it, raising the issue, I think is important. The issue that was raised that I think is important is the concept of fringe science. How do you, the non-scientist, or fan of scientists, or part-time scientist, amateur enthusiast scientist, like how do you distinguish, how can you distinguish between ideas and thoughts that are considered sound and justified and robust and agreed upon by the majority of scientists in the field, and, fringe stuff that doesn't make any sense, stuff that's junk, that's nonsense? One of the biggest challenges is that science, so many fields of science, is steeped in jargon. Think about the terms that I tossed around here, like the expansion of the universe, cosmic microwave background, redshifting, blue shifting, and Doppler, and on, and dark matter, and dark energy, and all the rest. I mean, it sounds like Looney Tunes, but it's not. So when a news story comes out that uses all the same jargon terms, and there's a lot of promotion, there's a lot of journalists latch onto it, seems to be written by a scientist, seems to be legit. How do you tell? How do you tell that it's fringe, or it's weird, or this is not established science, or it breaks everything we know about the universe? That responsibility for clearing the air, for showing you what's legit and what's not legit, is on the scientists themselves. I believe it's up to us as a community of scientists, to talk to the public more, because if the public hears from more legit scientists, it'll be easier for non-scientists to pick out, the wheat from the chaff, to pick out the junk and know what's solid. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter, and this show is brought to you by the Ohio State University Department of Astronomy. Learn more at astronomy.osu.edu. This show is also brought to you by you. Visit patreon.com/pmsutter to learn how you can keep the show going. Thanks to Greg Moebius for producing, Nancy Graziano for wrangling the Space Cadets, Dan Michalka for being awesome, and all the fine crew at WCBE Radio for making this show possible. We record every Thursday at 4 p.m. Eastern, whether I'm in the studio or not. We make it happen. That's right, Greg. We're a team. You can call 888-581-0708 to join me on the air, or leave a voicemail anytime like Greg did today, and we'll get it on the air. You can also catch the live streams on YouTube and Twitch and join the other wonderful Space Cadets. Go to spaceradioshow.com for all the links, show notes, old episodes, archives, everything. And of course, thanks again, Earthlings, for listening. See you next week, and remember, science is for sharing. End of transmission. Yeah, exactly, Commander Benkai. Thanks to all the people that do the actual work. I just show up, and I hit some buttons, and I start talking about science, and then some very, very talented, dedicated people turn this into a really fantastic radio show. And so I owe it all to them. Like, I really do. I'm so lucky. I'm so lucky to get to work with so many wonderful partners who share in this vision, who want to get science out, who want to make this happen, and are willing to do the hard work of overcoming those barriers to just get it out there, because I have no idea how to do it. I have no idea. I don't know how to make a radio show. I don't know how to make a good radio show. Don't tease me on that. But I just talk about science. It's people like Greg, Nancy, Dan that make it. And then, like the TikTok performance that I did in New York last week, I certainly don't know how to make a compelling dance performance, but I have cool partners like Siren Modern Dance, Lynn Peterson, Kate St. Amand, that are able to take that vision, shape that vision, co-create that vision, and make something really cool and compelling that we get to share with new audiences. So it's all down to the partners. It's all down to the people who share this. And it's all down to you. It's all down to the followers and the listeners and the Patreon contributors and the promoters, the people who say, "Hey, have you checked out Paul's new book? Hey, have you tried out this radio show?" It's I owe it all to you. I would not have the platform I do. I would not have the ability to speak to as many people as I do. I would not have the ability to share science in all the cool ways that I get to do without, the love and support of a fantastic audience like you. So, okay, Larry, Weird and Proud over on Twitch is asking me to wave my hand so I glitch out. So there it is. There it is. And now I'll glitch out. So thank you to all of you. And about that dark matter stuff that came up in the news, if you didn't catch me on Weekly Space Hangout last night, it's just wrong. It's just wrong. It's just junk. Negative mass doesn't exist in our universe. It breaks so many laws, not just laws of physics, but it breaks inertia and momentum. And yes, our understanding of inertia could be wrong. Our understanding of momentum could be wrong. Our understanding of mass and gravity could be wrong. For sure. But you actually need to show us a negative mass particle in order to even get the conversation going. And I don't know, it's just not going to happen. So that whole paper was just nonsense. Didn't get the results it claimed to get. It did not generate structure formation. It did not explain rotation curves. It did not explain an accelerating universe. It was just junk, but as a sexy title. As a sexy title, it uses all